My name is Paul Gölz. I'm presenting joint work with Avrim Blum on incentive-compatible kidney exchange in a slightly semi-random model. First, I will talk about kidney exchange, but more importantly, about our goal in this paper, to design mechanisms that control the incentives for hospitals when the matching takes the form of a long chain. Then I want to talk about obstacles that have held back progress on this front so far. And we think that this has to do with limitations of the standard models with which kidney exchange has been analyzed so far. Next, I will talk about the way that we found around these challenges. We introduced a new model, a semi-random model, and this model allows us to obtain non-trivial positive results. Finally, I would like to conclude with some takeaways. Kidney exchange is motivated by the many people worldwide suffering from end-stage kidney disease. In the United States alone, 500,000 people have both of their kidneys fail them, and they depend on dialysis for survival, which is a very taxing intervention. One of the few ways out of this state is a live transplant. That means that this patient here might have a friend or relative who still has both of their kidneys in good condition and who would be willing to give up one of their kidneys for the benefit of this patient. Often, the story doesn't end here because many kidneys are not compatible with many patients. Because of this, in the late 80s and 90s, economists called for the creation of kidney exchange clearinghouses that would allow many of these patient-donor pairs to sign up, to surrender their medical information that allows to determine which of the donors are compatible with which of the patients, that can then organize matchings or exchanges. So for example, here you have two pairs where the arrows are supposed to represent that the donor of the first pair is compatible with the patient of the second pair, and the donor of the second pair is compatible with the patient of the first pair. In this case, the clearinghouse could schedule a matching as the following, where they trade kidneys, and both of the pairs would be satisfied because they gave up a kidney but received a compatible kidney in exchange. This work on kidney exchange has had a tremendous impact in practice, and today there are 3 national clearinghouses in the United States, as well as clearinghouses in many different countries around the world. This contact with practice has also unearthed some problems that the original proponents of kidney exchange did not think of. And today I would like to talk about 2 of them that were presented by Itai Ashlaghi and Al Roth in 2012. They present 2 challenges: incentives for hospitals and long chains. Let me first talk about the incentives for hospitals. So far, my account of kidney exchange has really just focused on this compatibility graph, where, to recall, the nodes are patient-donor pairs, and the arrows correspond to compatibilities between a specific donor and a specific patient. But this graph alone ignores a specific bit of information about the nodes, namely that they belong to different hospitals. Why is this important? Because typically the patient-donor pairs don't sign up with the clearinghouse themselves. Instead, they're customers of a hospital, and it is the hospital's choice which of their pairs they want to sign up with the clearinghouse and which ones they don't. So we should really think of this graph as being partitioned across hospitals, here Hospital 1 and Hospital 2. And these hospitals then get to choose which parts of the graph to reveal to the clearinghouse. So for example, they might hide these nodes, and then the clearinghouse only sees the subset. Why might the hospitals do that? It is well documented that they do that in practice, and it has been hypothesized that a hospital simply feels more bound to the well-being of their own patients than to the patients somewhere else. And that means that if through internal matchings or just through getting a better deal out of the centralized mechanism, if they feel like they can get more of their own patients matched by hiding some of the nodes, they will do so. And Ashlaghi and Roth recommended looking at this problem as one of mechanism design, where such incentives to hide nodes were explicitly controlled. The second challenge that Ashlaghi and Roth brought up is about long chains. In the early research on kidney exchange, matchings took the shape that I've shown you before, of a combination of small cycles of length 2 and 3, and there are both medical and legal reasons why these matchings are very convenient. But in practice, another form of matching has become very important, that of a long chain. This also points to another way in which this view of just this compatibility graph of patient-donor pairs is not quite complete, because there is another entity that the clearinghouse can sometimes match. Sometimes there are donors that we call altruistic donors, or altruists, which are called so because they're willing to surrender one of their kidneys without requiring a kidney for any particular patient. What this allows the clearinghouse is to perform an exchange that takes the form of an arbitrary length path starting at this altruist. For example, this one. And so the kidney of the altruist will go to the first patient, then the kidney of the first donor can be given to the second patient, and so forth. And it has been shown that these chains can lead to higher welfare, so to higher numbers of patients overall receiving kidneys. And Ashlagi and Roth encourage researchers to think more explicitly about matchings of this form. In this paper, we will try to combine both. We will do mechanism design, so we will control for the incentives of hospitals, and we will assume that our matching takes the form of a long chain starting at an altruist. We will only be considering a single chain and a single altruist. I hope I've been able to convince you that this combination of incentives and chains is well worth studying. This raises a question, however. If the paper by Ashlagi and Roth was published 9 years ago, how come that mechanisms like the ones we're proposing right now haven't been proposed earlier? We think that the answer has to do with the standard models using which kidney exchange is typically analyzed. I cannot go into a lot of the details, but I would like to draw a rough distinction between models that consider random graphs and papers that consider worst-case graphs. When I say random graph, the main feature that I'm thinking about is that the question of whether two nodes are connected by an edge or not is made independently with a certain probability. And traditionally, these probabilities were typically chosen constant. But in the limit of large graphs, which is what we're talking about today, this leads to very structured graphs that don't seem to replicate a lot of the features that make kidney exchange hard in practice. Because of that, some of the research has moved on to sparser random graphs, where the edge probability is on the order of 1 over n, meaning that the expected degree of a node is constant. This still is tricky if we want to analyze incentives and long chains. If this constant degree is too large, then with high probability, there will exist paths that connect all the nodes that you might want to connect in a path. And this makes incentive compatibility nearly moot, because if the clearinghouse can choose certain paths that make everybody maximally happy at the same time, the incentives are no longer misaligned, and there would not be any significant reason for hospitals to misrepresent their nodes. This is not what we're seeing in practice, and so is not able to really elucidate the setting that we're trying to investigate. If this constant degree is too low, on the other hand, then the random graphs risk being very insular and not very connected. And that means that long chains might simply not exist. And so this model might also not be all that well suited to gain insights into incentives and chains. This is definitely not exhaustive, but maybe this gives you a flavor of how, in a certain sense, these random graph models just lead to very specific and predictable kinds of graphs that have a lot of structure that seems to limit how much we can actually say about the problem that we set out to analyze. As computer scientists, we of course always also have the choice of analyzing worst-case graphs. And worst-case graphs definitely don't have these same problems. Something that holds for a property that holds for worst-case graphs is very easily applicable no matter what these compatibility graphs look in practice. But the problem here is that worst-case graphs are in some sense too general, because they are very stubborn counterexamples that are hard to get around. Let's consider one of them. Here we have two hospitals, Hospital 1 and Hospital 2, and an altruist within the domain of Hospital 1. If k is an integer that goes to infinity, it is not hard to see that what the mechanism should go for is a path that looks like this one, which has a length of 4k and is much longer than all the other paths in the graph. This graph, however, will make Hospital 1 very unhappy, because only k plus 1 of their nodes are being matched, even though it would be possible to match 3k of them. And so Hospital 1 now has a very big incentive to pretend that the pair X has never signed up with them in the first place, which all but forces the mechanism to instead reward the hospital for its manipulation and choose this long path of size 3k. And while I've presented this in a somewhat sloppy way, this can be generalized into quite a robust impossibility result that shows that either your mechanism sometimes has to choose matchings has to choose paths that are way shorter than what would be possible, or sometimes it will give rise to very large incentives of manipulation. As mechanism designers, we're now in kind of a pickle. There were these random graph models that were just too specific and too narrow to study the setting that we set out to study. And the worst case graph model, in some sense, is too broad because everything just gets overshadowed by these impossibilities. And so it's hard to say anything other than, in general, it doesn't work. So how can we still move forward? The way that we propose doing that is by introducing a new kind of model that lies between the two, a semi-random model. And the claim would be that the semi-random model is not as narrow as the random models, but it somehow still has to take some of the edge off the counterexamples like the one that I've shown you. What do I mean by that? In our semi-random model, we still start with the worst-case graph partitioned across hospitals. There are no restrictions on this graph, so it can be as dense and sparse in different parts as it wants to be. But then what we do is that we introduce a low number of random edges between the different hospitals. Formally, we look at every pair of nodes owned by different hospitals, and with a small probability and independently, we insert an edge if there wasn't one already. Of note here is that this probability P is much lower than the probabilities that I talked about for the random models. We think of this probability as going to 0 faster than 1 over n, but not quite as fast as 1 over n squared. Easy consequences of this choice are that only a vanishing fraction of the nodes will have any adjacent random edge, and that the total number of edges that we introduce is sublinear. So maybe this gives some credence to the claim that that our model is way less narrow, and that the structure of the graph will really depend on the worst case graph that you start out with. It will not be mainly determined by the random edges that we introduce. But then how can this help? Because these few edges will not create long paths on their own. So the thing that allows us to get around are situations like the one we saw in this counterexample. What made this counterexample so annoying and hard to deal with and maybe unrealistic was that there were these long paths within each hospital's components. So in some sense, these hospitals have a very high connectivity. But at the same time, the connectivity between these hospitals was incredibly poor. And this effectively forced us to choose between making hospital 1 happy and between matching many pairs. Using these random edges, this is not quite necessary anymore, because with high probability, there will be a random edge from the suffix of the first path into the prefix of the second path. And this will lead to the existence of one very long path that makes both of these hospitals nearly as happy as they would be with their preferred solution. And this allows our mechanism to align the incentives and to get positive results. I'm not able to give more details on the workings of the mechanisms, but I want to give you an overview of what these mechanisms can and cannot do. Just to recall, the ideal properties that we would like a mechanism like this to have would be incentive compatibility, which means that a hospital cannot profit from hiding nodes relative to the baseline of revealing all the nodes. And the other property is welfare, because incentive compatibility is not that useful if the paths being chosen are all very short. We want the paths to be as long or nearly as long as the longest path starting from the altruist. We're not able to get these and to get these to perfection. First of all our results only hold with high probability, which is very natural given that our graph model is partially random. Incentive compatibility we can nearly guarantee. There can be some incentive for hospitals to hide nodes, but we make sure that a hospital can only increase its utility by at most lower order terms through manipulation, and hopefully together with outside factors and some amount of goodwill on the hospital side. This will be enough to convince hospitals to actually report truthfully. The biggest drawback of our mechanism is that we're not able to compete with the length of the longest path starting at the altruist. Instead, we're only able to compete with the suboptimal benchmark, the longest path starting at the altruist that does not switch between hospitals too frequently, which means that the ratio between the number of hops between hospitals' domains and the overall length of the path cannot be too high. So what should you take from this talk and from these results? I definitely don't want to claim that this mechanism is ready to be deployed in practice. For that, these mechanisms are way too tailored towards both the semi-random model and towards a specific welfare benchmark that we are trying to compete with. What these results do, however, is that they break out of this logic of this dilemma that I presented earlier, where both the randomized random graph models and the worst-case graph models seemed to be ill-suited to say anything useful and to elucidate and to gain insights and positive results about the setting. So hopefully, this approach and this agenda can somehow be brought further towards something that is more practical. I can't claim to know how to do that exactly, and I think this is a very hard question. My personal take would be that the biggest drawback of our mechanism is the weak welfare guarantee. At the same time, I would feel comfortable making the semi-random model a bit more stylized and inserting a bit stronger assumptions there. So possibly there are other semi-random models and other welfare benchmarks that allow for more practical guarantees. The final point that I would like to end with is that this approach using semi-random models is much broader than kidney exchange. Talking from experience, in my research, often when I see counterexamples for worst-case graphs or worst-case instances, I move on and ask other questions. But I think as an area, we would often profit from continuing to look into this. And semi-random models and other beyond worst-case methods are very attractive ways to still extract insights and positive results for these settings. Thank you so much for your attention.